Now, the next segment is we'll try to understand what is the fundamental operation which is performed inside these convolutional neural networks. Okay, and that is the convolution operation. So that's kind of funny. Later you will see that it's actually not convolution. All the libraries which you will see, they actually just use correlation operation. So if you want to call these like correlation neural networks, perfectly fine. It's just a term. But you also know, I mean, mathematically, it's not like a big deal, right? Both are almost same operations. And later you will see like why it doesn't matter whether you perform convolution and correlation. We'll briefly talk about that. Okay, so this is the core building block, the convolution operation, and also you can say the correlation operation. Okay, so what happens is we try to preserve the spatial structure of image. And if let's say this is your input image of resolution 32 cross 32. So this means that 32 pixels in height, 32 pixels in width, and 3 pixels in the channel dimension, right? So this is your input image. You have these filters. In this case, the shape is 3 cross 3 cross 3. All right. So these filters are weights of your convolutional neural network. So in case of neural networks, the weights were those arrows, right, which are connecting the input to the neurons to perform the linear combination. In case of CNN, these filters are the weights. And by weights, if you try to understand this, we don't estimate these values, we learn these values. Okay, so these filters will be learned from data, and that's like that's a very important point here. I mean, that's why these CNNs are very, very powerful. Because if we have to handcraft these filters, I mean, again, it will have some kind of biases, right? It won't be that powerful if you try to learn these on the data. So if we are training these filters on huge amount of data, so this learning is like automatic, which makes this very, very interesting. Okay, otherwise, this is same as like the classical algorithms, where, for example, Sobel algorithm, right? We have that kernel, which was not learned. We just use our knowledge, but still it was doing a good job. But in this case, we are learning these filters. So that's a big difference. So this filter is the weight of your CNN. And what you do is you convolve this filter on your input volume. Okay. So right now, what I'm showing you is this is an input image, but treat this as like it could be anywhere in your network. This could be this could be like your input image, or this could be like feature inside your network. Because as I said earlier, your CNN is actually transforming volumes to volumes. So you will go from volume 1 to volume 3 to volume 4. You keep transforming them. So this volume could be at any stage in your network. The operation is not going to change. It will be the same set of operation. All right. So in this case, it's input image, which is fine. So we have this filter. We will convolve this filter on this feature volume. So I will call this activation map or feature volume or feature map. All these mean the same thing. And you know how to convolve, right? So this is 3 cross 3 cross 3 filter. You will try to put this at like all the possible locations in this feature map or this input. And if you place, let's say at this location, so at this location, you will have again 3 cross 3 cross 3 volume from this blue cuboid. And you have like 3 cross 3 across 3 values from this kernel. You will just perform the element-wise multiplication. You will add those values, and that's going to give you just one number. So that's just a very standard correlation or convolution operation, which we have seen like a lot in this course. All right, instead of like 2D, it's a 3D. That's the only difference. Okay, so another point, you will see like this is called 2D convolution, right? But the kernels you are using, it's 3-dimensional kernel. The kernel is not 2D. Okay, so that's one thing to note. And if you are performing 3-dimensional convolution, your filter shape will be 4-dimensional. Okay, so now what happens is you take this filter and applying at one location gives you one value, but you just don't stop there. What you will do, you will apply at all the possible locations. All right, so you have seen like the sliding window approach. We have talked about that earlier. And that's going to give you an activation map or a feature map which will have like similar spatial structure as your input feature volume. So don't worry about the dimensions of this. So input was 32 cross 32, and this reduced to 30 cross 30. So we will talk about that, how the dimension will change. But at the end, you will get a lot of these values, right? Because you're applying at all the possible locations. So you create feature map using this. So this actually covers 2 points. One is we were talking about weight sharing. So you can see that we are just using the same set of weights or the same filter at all the locations to get this activation map. So that's how we are sharing weights. The second question was, I think someone was asking about programming assignment 1, that whether we want to preserve the shape of the input image when we compute the gradient. And of course, gradient is also filtering, right? So it's actually the same operation. So in this case, we are not preserving the weight. So we are going from 32 to 30. Okay, so this is like a single convolution operation inside your convolutional neural network, which is happening. And what you do is you don't just use one filter. You use multiple filters, and not just 2 and 3, a lot of these filters. So what will happen, for each filter, you will get similar activation map. Okay. So these set of filters represents one convolution layer. So when you're saying that, okay, you have a convolution layer in your convolutional neural network, so that convolution layer is nothing but these set of filters. And the operation that layer will perform is, it will take each filter, perform this filtering operation on all the possible locations, obtain this activation map, and repeat the same process for all the filters. So if you look at this, you are actually going from volumes to volumes. It's just like the shape is changing, which is fine. We'll talk about that, like how to preserve that or if you want to change it. But the bottom line is we're going from volume to volume and we are sharing weights. Okay, so your convolution layer, as I said, it's just like set of kernels. Now let's try to understand that using a very concrete example. Let's say we have a convolution layer where we have 6 different kernels, and each kernel has shape 3 cross 3 cross 3. This was your input image, height and width 32 cross 32. It has 3 channels. It's a colored RGB image. And this convolution layer, which has 6 kernels of this shape, will give you 6 different activation maps, right? Because 6 kernels, one kernel is going to give you one activation map, 6 will give you 6. And that's why the depth of this activation map is 6. And don't worry about 30 and 30. We'll talk about how we got from 30 to 30, but do try to understand how we got this 6. So this 6, the 6 is a result of like how many kernels we have. So if we would use like 60 kernels, the depth of this activation map will be 60. Okay, so that's one important thing. The second important thing which you should understand on this slide is the shape of this kernel. Okay, so as I said, we are performing 2-dimensional convolution, but the kernel shape is 3-dimensional. So the reason is the third dimension of this kernel, we have no control on that. Okay. We can only control the first 2 dimensions. So usually you will see that in your CNN, when you're developing 2-dimensional convolution neural network, you will only say whether the kernel is 3 cross 3 or 5 cross 5, 1 cross 1, 7 cross 7, because the third dimension is implicit. And the reason is the third dimension is actually determined based on the depth of your input feature map. In this case, image is the input and you have 3 channels, and therefore the third dimension of this kernel is, it has to be 3. So it doesn't matter how many kernels you use, for all the kernels, the depth will be 3. All right. And you can also only design the first half. So in this case, the kernel is 3 cross 3. Okay, so that's one important part. Second is like how you get the 6. So with that, I mean, if you have another convolution layer after this activation map, so one thing is predetermined. Irrespective of what is the size of a kernel, the third dimension of that kernel will always be 6. All right. So then what you can do is, this is one like convolutional neural network with one layer. You can just stack like these convolution layers on top of each other. Okay, so that's the first layer. Then you can add one more layer. In this case, the second layer is you have 16 different kernels. The kernel size is 5 cross 5. And you can see the third dimension we can't control. So 6 is coming from the depth of the input feature map. Because that was 6, that's why we have 6. And again, so this 16 will give you 16 different activation maps, and that's why we have this volume. Of course, the X and Y is actually going from 28 to 24, which is fine. As I said, we'll talk about that later. So that's how, so this is like a 2-layered convolutional neural network. You can just keep building layers on top of these. Okay, the layers, the operation will not change.